Hello everyone, welcome to the Digital System Architecture Practical Series. Today we'll be doing flip-flop implementation using SimulIDE. So let us start with the SR flip-flop. So this is how we make up SR flip-flop. We can make using 4 NAND gates, as you can see. So let us see the working of this SR flip-flop. So with 2 inputs S and R, we can make 4 combination. Let us start with the first combination as 0 0. Now to begin with this working, we may have some output, like let us assume we start that before applying input as 0 0, we already had some output as 0 1. So in flip-flop, we must note that the outputs are complement of each other. So one of the output Q is 0 and Q bar is 1. So with this output, what happens, let us see. So we apply the inputs as 0 0 and assume that previously we had the output as 0 1. Now because of the feedback, what happens is this one on the Q bar comes up to the upper NAND gate of the output and 0 comes below. So with inputs as 0 0, okay, so any input of NAND gate is 0, output becomes 1. So output of both the NAND gates of SRR, which are connected to SNR, are becoming 1. Now in the next stage, what happens is the output in the upper NAND gate, as we can see, 1 1 is 0 and 0 1 is 1. So output does not changes. So output which was 0 1, it remains as 0 1. Now let us start with again with 0 0, same inputs, but here now we are assuming that previously we are having 1 0. So if you remember, we assumed just in the previous slides as output as 0 1. Now we are assuming, suppose if we are having 1 0, what happens next? So with the same argument which we did previously, this feedback gives the 0 up and 1 down, and with both 0 0 we get again 1 1. Now here 1 0 in the upper NAND gate will give 1, because any of the input is 0, output becomes 1, and the lower NAND gate 1 1, it remains as 0. So what conclusion we draw is, with input as 0 0, output remains, Q remains as Q and Q bar remains Q bar. So with input 0 0, if the previous output was 0 1, it will remain 0 1. If the previous output was 1 0, it will remain 1 0. Okay, so we name this state 0 0 as no change. Now suppose we are having input as 0 1, okay, S is 0 and R is 1. So with this, what happens? So with this, irrespective of whatever output we are having previously, we get something like, we will see what we are getting. So with S, input of S equal to 0, it will make output as 1, and R is 1. So because 1, it is distributed to both the NAND gates, so 1 1, it becomes 0. Now in the lower NAND gate of the output, because we are having 0, this 0 will actually force the output Q bar to become 1, and this one will go to the feedback, the input of the upper NAND gate, and 1 1 becomes 0. Okay, so with 0 1, we have output as 0 1 irrespective of whatever output we were having previously. So 0 1 input, 0 1 output. This particular actually, of course, we are having this, of course, we have the feedback also. So of course it does not change. So this state is called as reset state. Why it is called as reset? Because Q becomes 0. So this is the reset state. Now with because this particular flip-flop is of course symmetric, like whatever we having in the upper part, we having the lower one. So with 0 1 we got 0 1. Of course with 1 0 we will have like output as 1 0. Okay, going by the same argument we did in the previous state. So with 1 0 we will have 1 0. Now because Q is becoming 1, okay, we name, so this is all we are having here. Okay, so we have this 1 0. So this is called as the set state. Okay, this is the set, because Q becomes 1. Now let us go for the last combination 1 1. Now with 1 1, the S, the upper NAND gate and the lower NAND gate, the output simultaneously will become 0 0, because both the inputs are 0. So with 1 1 input of NAND gate, the output becomes 0. Now with 0 input at both the NAND gate of the output of that particular gate, Q and Q bar, they will of course simultaneously become 1. Okay, and even if they are, we consider the feedback, the output will not change, it will remain as 1 1. Now because in flip-flop the output should be complement of each other, but here we are getting both the outputs as same, so this state is not allowed. Okay, so now let us execute this part using SimulIDE software. You can also use any other software. So now we are into SimulIDE. Let us select the component. First we select the AND gate, okay, and make it NAND, because we require NAND gate. Invert the input so it becomes NAND gate. Similarly, or we can do this one thing, we just copy and paste. So this is the thing. Now we require the inputs. So for input we have this fixed voltage, okay, source, and a fixed voltage source. Okay. Then for output we have the probe. We take the probes, 2 probes. Now we do the connection. First we need to just connect the input together, this one, shorting the inputs. Then connect, this is our S input, this is our R input. This gets connected here. This gets connected here. Sorry. Okay, so this gets connected here, and then this is the output. So this is the output Q, and this is Q bar. And then we need the feedback output of this connected to the other one. Okay, now we are done. Now let us start. Okay, so what we observe is we assume that we start with, let us start with 1 0. So for 1 0 we are getting output as 1 0. Now we're making as 0 0. So what we observe is output was 1 0, and with 0 0 output did not change. Let us make 0 1. Now with 0 1 output becomes 0 1. Okay, and then if we make this as 0, so 0 0 output does not change. Let us observe what I am saying again. I am making the input as 1 0, I got output as 1 0. Okay, and if I make both as 0 0, output does not, it remains in the previous state. Now if I make 0 1, I am getting 0 1, and if I make this again input 0 0, output does not changes. So the first 3 states are verified. 0 0 does not changes, 0 1 output is 0 1, 1 0 output is 0 1. Now if we make both as 1 1, output both become 1 1, which is actually not allowed. So in flip flop the output should be complement of each other. So this is how we verify the SR flip flop. Now let us go for the D and then JK flip flop. Now before proceeding to D flip flop, this is just a summary of the SR flip flop, the truth table of SR flip flop. For 0 0 we have Q and Q bar, so it is no change. For 0 1 we have 0 1, so it is reset. For 1 0 we have 1 0, which is set, and 1 1 it is 1 1, which is actually not allowed. So both the output should not be same by any circumstances. Now let us see how we can convert the SR flip flop to a D flip flop. Now this is the SR flip flop which we saw in the previous slides. Now we can actually make this one more easier by drawing the block diagram instead of using all the gates. So it becomes it actually clears the understanding. So what we do is replace this by the block diagram of SR flip flop. Of course it has 2 inputs, SR and Q bar. So this is the block diagram representation. Now let us see how we can convert SR flip flop to D flip flop. So what we do is, in case of D flip flop we only have one input, so we get rid of this particular input of the R, and what we do is we connect a NOT gate to the R. So we only have one input, the input goes directly to the S and it goes to R through a NOT gate, and we name it as DIN. Only one input is there, DIN, and at the output end we only use the Q, so we have this is D out. Now let us see the working of this. So we only have, because there is only one input, only 2 combinations are possible, 0 and 1. So let us see what happens with 0. With input 0 we get this 0 here, and 0 goes below, and because of the NOT gate this 0 comes to converts to 1. So input 0 1, so input is 0. For SR we have output also 0. Okay, so input is 0, output is 0. So if you remember the SR flip flop, for 0 1 we are having 0 1, so here we are only having one output, so it is 0 output. Then if the input is 1, this one goes directly to DIN, and through a NOT gate we get it here as 0. So 1 0 is 1. So if we observe the truth table of SR flip-flop, the second and third inputs 0 1 and 1 0 are utilized. So input is 1, output is 1. Now let us verify the working of D flip-flop using the SimulIDE software. So this was the previous circuit which we saw as SR flip-flop. Now let us see how we can convert this into a D flip-flop. So what we do is we just get rid of this input. We only have one input here, and what we do is we just connect. We take one connection here, and we need a NOT gate actually. So let us take a NOT gate, and then we can so we take a buffer and convert this buffer inward output. So now this becomes the NOT gate. I just keep it here, okay, and do this connection, okay, and this is connected here, and of course we don't need this, okay. So we only have one input, one output. Now let us, this is now the D flip-flop. We have converted the SR flip-flop as a D flip-flop. Let us start. So this is running. So input 0, output 0, input 1, output 1. So for 0 we get 0, for 1 we get 1. So this is how we verify the working of a D flip-flop. Now let us go to the JK flip-flop. Now before starting with the JK flip-flop, let us study the concept of the clock. So clock is a sequence of alternating zeros and ones which are used to synchronize and control the timing of operations in digital devices. It is acting as a heartbeat of the system. So we have a clock generator. It generates a sequence of zeros and ones, as we can see here. So we have something called as the rising edge, in which the clock transits from 0 to high, that is from low to high state, and there is a falling edge where it transits from high to low. So why this is important? Because many of the flip-flops in which we are using the clock, generally we use clock with the flip-flop because they are sequential circuits. So in that case, this rising and falling edge, they are important because some flip-flops they trigger on the rising edge, some trigger on the falling edge, and of course some are also level triggered. So this is the thing. Now this is a clock generator. When we turn it on, it generates a sequence of pulses, as we can see here, okay, until we stop this clock. Now let us see the JK flip-flop. So this is the logic diagram of a JK flip-flop. Now it is almost similar to SR, only the difference is that the feedback is given also to the two first NAND gates where we are applying the inputs. So that is the difference. So the feedback Q and Q bar, they are also applied to the output NAND gates as well as the input NAND gates. So let us study this. So with the first input as 0 0, we are applying the inputs at 0 0. So it may happen that there may be some outputs already. So let us assume that we have output as 0 and 1 before applying the inputs at 0 0. Now because of the strong feedback, this 0 is coming at the feedback of the output NAND gate, the below, as well as the input NAND gate, the lower one. Okay, so this both becomes there 0 0 because of the feedback. Similarly, this one comes at the feedback of the upper NAND gate output, the output NAND gate as well as the input NAND gate. Now because in case of NAND gate, even if a single input is 0, output becomes 1. So output of this NAND gates both become 1 1 simultaneously. Now if we observe the output, what we have in the lower NAND gate, 0 1 will give us 1. Okay, this 0, because of this 0 output becomes 1, and in this case both the inputs are 1 1, so output becomes 0. So it started with 0 1, we got 0 1. So with 0 0 input, if the output is 0 1, we get the same thing output as 0 1 itself. Now with the same argument as the previous one, if the output had been 1 0, we would have got the 1 0 itself. So in other words, we say that when the input is 0 0, the output does not changes, it remains in the previous state. So Q remains as Q, Q bar remains as Q bar. So this state is called as no change. That is what we got in SR flip-flop also. Now what happens if we give 0 1? Okay, with this input 0 1, the upper NAND gate, it gives 1, because even if a single input becomes 0, output becomes 1, and in the lower case, the lower NAND gate, because there is one input, okay, so output becomes 0. Now because of this 0, the output of this NAND gate becomes, the lower NAND gate becomes 1, okay, and upper, because it is 1 and this 1 is coming the feedback, so the output Q becomes 0. Now this Q is coming as a feedback, so 0 0 is of course 1, and this one is coming as a feedback, so 1 1 is 0. So with 0 1 the output is 0 1. Okay, so this is called as a reset state because Q becomes 0. Now if the input is 1 0, because this is a symmetric one, in the previous case with 0 1 we got 0 1, so with 1 0 of course we'll get 1 0, so no need to explain this again, this was as previously explained. Now this is called as a set state because Q becomes 1. Now what happens with 1 1? Now this 1 1 was not allowed in SR, but it is allowed in JK flip flop. So with this 1 1, what happens? So let us assume previously we had 1 0. So before applying 1 1 we had suppose 1 0, and because of this feedback this one is coming back and this 0 is also coming back here. So next what happens? Suppose the next clock arrives. So because of this 0 the output of this NAND becomes 1, and because of this both 1 1 and the clock, this becomes 0. Now because of this 0 the output of the next gate becomes 1, and this one is feedback here, so this 1 1 makes the output as 0. So we started with the old state as 1 0 and we got the new state as 0 1. So this is the new state 0 1. So we started with 1 0, we got 0 1. So if we continue this operation with every clock pulse, the output will flip from 0 1 to 1 0 0 1 1 0. So this state is called as the toggle state. So this is how the JK flip flop works. Now let us simulate this using the simulator. So now we are into the SimulIDE. So how to select JK flip flop? So we just click on this memory. You can see below the gates and everything we have this memory, and in memory we can find the flip flops. So I'll just click on this flip flop and take it here. Okay, so this is this is the JK flip flop. Okay. So we need to connect the inputs. So we have this fixed voltage source, we'll use this as the input. Okay, and then we need a clock. So this is the clock. Okay, we place it here. Then for output we have a probe, so we connect this probe here, then another probe here. Now in this case this S and R, you can see set reset, we can actually preset and clear, this option is there. So we need to connect this fixed voltage source, keeping it high. Okay, otherwise this flip flop will not work. So we need to put this S and R. This S and R are called as preset and clear. Now in this case we need to make them as 1, otherwise this flip flop will not function. So next we do is we connect this J, the upper input as with J, the lower with the K1, and the clock here, and then this to the probe and this to the next probe. Now I just start the clock, and of course we need to do one more thing. Double click on the clock, and yes, we can see the frequency is 1000 Hertz. You can see this is Hertz. I'll keep it as 5 Hertz. Now the reason is in the last state, toggling state, it will start toggling at a very fast rate, so we need to slow down the speed, so we need to keep it 5 Hertz. Okay, so this should be Hertz, not kilohertz, it should be Hertz, and this is 5. Now let us start. Okay, I'll just start the clock. Okay, and then we can give this input. Okay, I just start this. Now it start running. So with 0 1 we are getting 0 1. Okay, with 0 1 we are getting 0 1. Now if I make it both as 0 0, so 0 1 remains as 0 1. Now if I make it as 1 0, output becomes 1 0, and if I make it 0 0, output remains as same as 1 0 itself. Now what happens when we make both as 1 1? Now see it both at 1 1, the output starts toggling, it becomes 0 1 0 1 continuously. So this is the last state, that is the toggle state. So this is how the JK flip flop works. So that's all for this particular session. Thanks for watching. Do join us for the next video.